So up next is a discussion about BMCs and the root of trust and how they work together. So we have Benjamin is here from OpenBMC, and Garrett Kelly is here from the OpenTitan project. And so we'd just like to give each of them a little bit of time to talk about their experience in integrating the BMC and the root of trust so far, and then I'd also like to talk about what OCP can do to help in terms of making this easier if we need to, like standardizing APIs or physical interfaces or things like that. So Benjamin or Garrett, can you talk about your experience a little bit?
Sure. So just to introduce myself, so I'm Benjamin. I work on Google's GBMC team. I'm one of the tech leads there. So we adapt and implement OpenBMC for the Google platforms that we work on. So part of that is integrating things with the root of trust that's used at Google. So some of the things that some of the issues that we've noticed when trying to do this integration. So first of all, we use a SPI as our interface between our BMC and a root of trust, which has some things that make it not ideal for that. So there's no flow control, for instance. You have to be immediately ready whenever data is requested or sent. So the root of trust, if it can't keep up, it has no way to pause the data or tell it to wait longer. Along with that, there's really strong timing requirements that make it difficult to, say, do a deep inspection of the data that's flowing into the BMC, or to edit it on the fly in the root of trust, which are some features that would be very useful from a security perspective. With SPI specifically, the API on top of it is not fully standardized. There's lots of differences between manufacturers. So one thing that always crops up that hurts us is 3-byte versus 4-byte addressing. Knowing which addressing mode we're in, switching back and forth between them, which manufacturer-specific commands should we use, all that kind of stuff inevitably crops up. So Garrett, do you want to talk a bit about the root of trust API also, the SPI versus something else?
Yeah, sure, absolutely. So I'm Garrett Kelly. I am the software lead on the OpenTitan team inside of Google. And so we're a fully open source project, so we have less integration with Google than you might otherwise suspect. But one thing that has come up a lot with the electrical API to the root of trust, the things that Benjamin has said are absolutely true, especially when it comes to things like our ability to introspect SPI traffic on the fly. So in a lot of integrations, there is a root of trust sitting between SPI flash and the BMC, and that's how you get first instruction integrity. Is you inspect the SPI flash, ensure that it's signed in a way that you like, and then allow pass-through reads to it. And there's a lot that prevents you from doing this in a very secure way. Specifically, as Benjamin said, you can't inspect it on the fly. You have to be able to turn around that message instantaneously in like combinatorial time, as opposed to being able to exert back pressure and say, oh, actually, wait, I'm going to build up a verification of this message, or I'm going to do additional validation before sending it on. And so there has been some discussion with, at least in our team, about using directly the TPM SPI protocol layering, so allowing us to exert back pressure via that control mechanism. But I think that it would be nice if there was a mechanism which was universal, or even a bus which was a little more universal. And there have been suggestions that I've heard about using USB embedded, or USB 2 embedded, or USB 3.0 to do the actual interface to the RoT. But unless we significantly increase the complexity of the RoT and BMC stack and the analog side of the RoT, I think that adds a lot more problems than it subtracts, to be honest. If you're talking about a memory attached storage device that your bootloader needs to be able to read from inside of your BMC, you're now talking about putting a USB stack inside of the bootloader, and putting analog integration for USB, and and being able to either simulate the other side of that mass storage device, or otherwise intercept that USB traffic at the RoT stage. So I think that there's a lot of good questions here about how we make this work and how we get away from these old buses, which old buses are the wrong buses for the jobs, and move to a protocol where it can actually exhibit back pressure. I think that there's promise in some of the upcoming bus tech, like I3C is looking promising to me. I'm not 100% convinced on it yet, I guess, but that's just me not having spent enough time reading the specifications. Benjamin, have you actually looked at I3C on the BMC side yet?
So I know that some of the next generation BMCs are most likely going to support it. I think that was targeting like some of the new DDR specs, for instance. But I haven't looked in detail into using it as an API to the root of trust. Although one interesting proposal for that is using like SDHCI as the protocol used by like SD cards or eMMC. So a lot of BMCs have a native controller for that protocol, and that does exhibit some of the like flow control and blocking semantics that we might want, and it's a stronger API compared to SPI. So that's a proposal that I thought of or come across.
Oh, that's interesting. From an electrical standpoint, that doesn't cross into the same kind of extreme agony of USB 3 in terms of the analog domain, which is nice as well. And it is actually fairly few electrical signals. I think SDHC is only 6 electrical lines, if I remember correctly. So that's interesting. I hadn't heard that proposal yet. That's a neat idea.
Yeah, and some of the new BMCs, either you can have a minimal bootloader through SPI that, say, the root of trust could host out of ROM, and then jump directly into eMMC, or possibly even boot directly from eMMC with no SPI attached whatsoever.
eMMs. Oh, sorry. Go ahead.
Oh, I was going to say the multi-stage approach like that seems like it would work with almost any interface, though. Like if you can load a very small, like first boot image out of SPI, and then why not just boot off of like SATA or anything else?
Well, there's no native SATA controllers in the BMC, but you could attach one to like the USB or PCI Express buses in the BMC and then have that read to the root of trust, but adds extra board complexity.
Or, I mean, you could even boot off of another larger SPI device at that point, as long as your early boot image is able to do all the verification. Why not just have 2 SPI interfaces then?
Yeah, I think you still have the same time of check to time of use problem with the first smaller SPI interface. So you can't on the fly do that verification unless you add a significant amount of complexity to the RoT. It means being able to turn around the validation and then pass through of a single message in like nanosecond scale, like fully 24 megahertz line rate, and so that's very, very difficult to do with a general purpose like Cortex M0.
Well, I mean, Benjamin specifically said hosted in the ROM of the root of trust.
Yeah, if you can make it small enough.
So if you can make it very small and host it internally, then you get rid of that problem.
Absolutely, yeah. If you can establish implicit trust because it's in mask-ROM, absolutely, that would be, or even on die, then yes, there's.
Well, not necessarily mask-ROM, but if the root of trust can store it in internal flash, so it can pre-verify everything and just be ready to go.
Yep, yeah, that is one approach to first instruction integrity. Absolutely. I think some of the big nodes that are being used, these smaller nodes that are being used for BMCs don't necessarily support flash text, so you end up with like multi-package on die, which does increase your cost, but that is an approach for sure. There's even a path forward here if you're looking for high assurance of the identity and integrity of the device. There is a path forward here to doing integrated RoTs as well. So you have your RoT on as integrated IP in the BMC. It inspects first boot code, then passes that off. It still provides protection for the identity because it's not sharing memory, it's not sharing buses. Yeah, there's definitely some interesting things that can be done when you talk about high integration like that.
Yeah, that would unlock a lot of more possibilities. But yeah, BMC specifically, since you could potentially boot directly from it with no multi-stage, no initial flight, is a interesting idea. So we actually also have the same kind of problem when we're trying to like transitively establish trust for the host from the BMC. So we have like a even worse technologies vulnerability if we try to just mux out the flash from the host BIOS flash to the BMC verify it. So it's also an active area of investigation, like what technologies we could use to have the host boot directly from the BMC and eliminate that extra BIOS flash chip that can't really be fully trusted.
Right. Yeah. That's a really interesting approach too. I mean, I always think from the root of trust side. So I always say, like, once we've passed off to our next level, so mainly in our case BMC, then we're done. But there's a full stack past that to be involved with. So being able to have the BMC be the storage technology would be pretty interesting. Is there anybody on the market right now who's doing that, who lets you actually host the image from, or like provides a flash simulator on peripheral, or is that something that's just still experimental?
Yeah, so IBM Power CPUs actually allow this through their FSI interface. You boot fully from the BMC, because the BMC is a lot more involved in the boot process there. On Intel, they have this extension to eSpy called SAFS, but it's not widely supported. It would allow the host to boot from an image hosted by the BMC from its DRAM, for instance, rather than having to boot through a real SPY flash. Yeah, like I said, there hasn't been much industry adoption of that yet, and so it's not widely supported.
Yeah, it was my kind of understanding that there was kind of like two SAFS spec versions, and that they're not compatible, and there are two chipsets that use them, but it means you have to choose one to implement. Is that accurate, or am I haven't had much experience with this SAFS, to be honest.
Yeah, so that was I think what you're referring to is on the ASP 2500 BMC, the currently available chip from the main BMC manufacturer. They had implemented version 0.75 of the eSpy spec, whereas Intel ended up going with version 1.0, which made a couple of changes, and that caused it to be incompatible with the released versions of Intel PCHs. That should hopefully be resolved in the next version of the ASP BMC, which could make this approach possible again.
Nice. Yeah, it'd be nice to see like at least compatible alignment there. I know that we have people on our team looking at SAFS as one of the options, but because we don't see other chipsets with the capabilities for that right now, I think we have kind of calmed down on that and are still focusing on SPY in terms of OpenTitan for pass-through.
Yeah. Even if it is supported on the BMC, it still is only an Intel feature at this point. So it could be better to try to come up with the entire industry can agree on for this boot interface, and potentially even reuse the same thing for BMC to root of trust if the protocol that we end up going with is the protocol that we can converge the industry on is not too complicated to implement in root of trust silicon.
Yeah, I don't think it has high analog requirements for RoT silicon. So is my understanding for SAFS. So I think it's doable. Still requires some controller work, is my understanding, just to get the high-speed signaling down. But like you can't bit bang it, is my understanding. But still an interesting area to look at for sure.
There's a question in the chat of would the use of Ethernet for inter-IC communication be too futuristic or expensive?
That's a good question. I think personally, this is just I would couch this as my personal opinion. Ethernet, in terms of inter-IC communication, you have to strip out the PHY. You can't do it over the regular Ethernet PHY 802.3x. Is that what it is? Because it has very aggressive signaling requirements. You need transformers to actually do the Ethernet PHY signaling, and it's a big board space constraint, and those are like signals you need to take very special care of. I wonder if you couldn't do it before the PHY, if you couldn't send post PHY pre-hardware, post mid-PHY, do a mid-PHY signaling approach where you could actually use Ethernet framing to talk to the other devices, but didn't actually need to use the full Ethernet PHY. I think being able to plug an Ethernet cable in and connect it to another device is too onerous for the RoT. You need too much either die space or external components would be my statement there.
So Garrett, just we do a lot of Ethernet. There are backplane Ethernet standards that are CERDAS based. The KR is one of them, and you can build 100 megabit transformer-less Ethernet infrastructure. Yeah.
There you go. Somebody smarter has figured this out. Then that's me. I mean,
if you look at a lot of the networking equipment, many of those chassis have Ethernet connectivity to all of the different pieces in the system.
That's interesting. I wasn't aware of that. Do you end up integrating this half PHY into the actual silicon, or do you use that off chip and still talk to it over?
So there are standards of being able to do transformerless 100 base T, and then you have an Ethernet switch on the platform someplace, or you do KR, which is a SerDes based infrastructure, where you can do essentially raw Ethernet frames over something that looks like a USB 3.1 interface from a PHY perspective.
Right.
But that usually also requires a switch someplace. Yep. So you're really trading switches for hubs. I mean, big picture, that's what it would come down to.
Right. I mean, at least those are well defined. Like unlike SPI multi-master configurations right now, where you're hoping that you're not shaving frames, you're hoping that you're not getting half responses that are going to tickle other pieces of your hardware. At least there's a definition for it.
Right.
Yeah. That's interesting. I had not realized that was actually widely deployed. I will go read up on that for sure. Thank you for that. Speaking of electrical signaling. Benjamin, I have to ask, what other signals are you interested in on the BMC side?
Oh yeah. So one of the most important signals that you don't always get from a BMC is just a signal saying that the CPU has reset. So knowing this information is critical for the root of trust, because it tells the root of trust that it should verify the contents of the BMC again, the boot flash. Otherwise, the BMC could start running malicious firmware by resetting into it without anyone noticing. There are signals that we
sort of more specifically, that has to be a completely hardware-based signal.
Yeah,
so
exactly.
Like a watchdog timer or something like that that can be changed by firmware isn't good enough.
Yeah, something that is only controlled within the silicon that can never be overridden. Yeah, and then from the other direction, we also need signals that will reset or force the BMC to reset. So one that can put the whole chip into reset, like a big hammer we call it, is useful to put the system back into a known good state, or to hold the BMC fully in reset while the root of trust is verifying the flash. And then we can also sometimes use like a smaller reset that just resets the CPU core if we don't need to bring down the whole system.
Is there anything else that you wish you had from the BMC side? Like, is there a wish list?
I don't know, maybe like a signal that says when the BMC is leaving ROM and like executing code from RAM now. Could potentially be useful. What else? Yeah, if I think of something else, we can come back to it, but I don't have anything else off the top of my head.
Sorry to put you on the spot there, but I was thinking I've seen in phone integrations for roots of trust that it's actually implicit that signal you watch for reset. Once you see reset happen, then you know the next component that you are talking to is going to be the first stage bootloader, and so you can trust it to faithfully tell you that it is the first stage bootloader until it tells you that it is about to leave, and then you can trust nothing else from that point forward. But I understand the desire for a signal there so that you have, you know with confidence what you are talking to because you know the integrity of the mask instructions. I like that.
Yeah, yeah. What else?
I think one thing that I've been talking about. Oh, sorry. Was there somebody else there? Sorry.
Yeah, I posed the question, but I'm on the Zoom, so let me just ask. I think at the high level, do you see the root of trust for the platform and the BMC converging into one, or do you see them as always staying separate?
From my perspective, I think that they will converge eventually. I think that there is probably a very good story about putting a root of trust IP into BMCs, being able to have that hardened identity, hardened ownership transfer properties, hardened machine first initial instruction integrity is an interesting thing, and I think that making it a commodity piece of IP, it makes sense. That's my feeling. I don't know, Benjamin, maybe you feel differently.
Well, so does that create any security concerns with supply chain integrity? Since like if you have two separate chips, then you have two separate supply chains. So you might be able to secure just the one for the root of trust better. I'm not sure if that's a concern or not.
That's a good question. I mean, you do have to now cover your BMC manufacturing with the same level of assurance that you would have covered your RoT with. And if you're talking about things like personalization and identity injection, yeah, you're now talking about HSMs being attached to your BMC. You're adding extra manufacturing time for your BMC, but you can now completely sacrifice the entire root of trust line. You no longer have to worry about that for root of trust. You have to treat the BMC as if it is also the root of trust because it is now the root of trust. So I think there's actually a benefit there. Now, given that the scale of integration for a BMC is much higher, I do have to wonder if that increases the cost significantly for it. But I don't actually know. I would suspect that all in all, this probably reduces the total cost of integrating an RoT and BMC onto a machine. It reduces the cost from integrating a discrete RoT and BMC to just have an IP-based RoT inside of the BMC as well.
So I also wonder about
challenging. One thing that is more challenging with that is the BMC is significantly larger, and so verifying that your root of trust is logically separate from the rest of the BMC is much harder then, because we try to make the root of trust as small and isolated as possible so that it's much easier to not make mistakes in it, because the smaller it is, the easier it is to verify.
Yes. Yeah.
So integrating into the BMC does make that aspect a lot more challenging too.
Absolutely, and there are other challenges too in that the technology node that you're using to build the BMC probably or usually doesn't have a flash macro available for it, and so you're now looking at doing multi-package, as I said before, and that on its own is more vulnerable. Like to being able to reach in and see a discrete flash package and grab those interface lines, that is a much easier task than reaching into a discrete RoT and touching its flash, which is already integrated as a macro, might be underneath shielding, might be already be part of the integrity protection of the system. Yeah, there are definitely challenges to that integration.
If you
are there other specific manufacturing techniques that are used on a root of trust that would be more expensive to have to apply to an entire BMC?
Yep, absolutely. Yeah. So in terms of physical protections, you usually see something like a shield layer or a top layer or even a top and bottom layer being dedicated to protecting the device from probing, or being able to, if not protect, then detect the probing attempts for into the device. Putting those over the entire area of a BMC die would be expensive, and I don't even know possible. I think the BMC nodes that I have seen being built are using all of the layers currently. I don't know if you can stack up another layer that easily on top of the BMC.
Yeah, so that could make it more expensive to integrate. So unless you do like dip in the same package, which has the same issues that you mentioned.
Yeah. And now you might be able to get away with doing the protection shielding layer just on one part of the BMC die. You might be able to shield just the RoT components, and that might be feasible to spend your effort there, spend your technology on that one area when you know that it will be providing the root of trust for the rest of the system.
Yeah. Do you want to talk about the software level APIs too?
Sure, absolutely.
The other interface.
Yeah, that's a fairly big question these days. Like, how do you talk to a root of trust? How do you integrate with a root of trust? The on OpenTitan, we're actually working on building a Cerberus implementation in Rust. It's called Manticore. It's fully open source. You can go github.com/lowrisk/manticore and follow along. We're working with Microsoft in a discussion to try and move forward the interface to Cerberus. Right now, Cerberus does hard specify MCTP over SPI, and this has some of the downsides of SPI as we discussed before. But we think that there is an opportunity here to be able to turn this into a multi-transport, or a transport-agnostic root of trust API, in order to deliver the kind of guarantees that Cerberus gives you, but on integrations which don't require SPI. And so we're, as I said, working with Microsoft on that, working on an open source implementation of that. OpenTitan is at its core agnostic. So we don't actually believe you should run one API or another. We just want to come up with a way that if you don't have an API, or you have a question, which API should we be using? That we have a solution off the shelf, so that you can come in and say, okay, we'll use Cerberus. We'll take Manticore, we'll run it on your reference stack, and be able to have an RoT API off the shelf. I don't know. Sorry, there's also, I guess, a question there. How does that integrate with a BMC? What do you want from a BMC in order to be able to integrate with an RoT? We think that the protocol services is nice enough that we can put it over pretty much any link, and so being able to speak it from a BMC isn't that far in the future for us. We haven't done that work yet, but that's part of some of our pilot work for BMC integrations.
Yes, I've seen some other people in the OpenBMC community start to integrate with APIs for roots of trust. I think generally it's like TPM rather than the type of root of trust that we're discussing. So the interfaces aren't necessarily the same, but there's definitely room for collaboration there with other members of the OpenBMC community to try to define a common framework for talking to a root of trust, regardless of what API we're using, whether it's something based on Cerberus or some other API. So you mentioned that this is implemented in Rust. So you're able to run Rust code on the root of trust CPU itself?
Yeah, we actually, our operating system is written in Rust. Our operating system is called Talk. It started as a research project by a person named Amit Levy. Google hosted several interns, and when I say interns, I mean like fairly high-level people at some universities, in order to be able to continue to develop on this and invest in Talk. And it is actually the basis of our reference platform. So we run this OS, this Rust-written OS Talk, and then on top of that, we are running Manticore, which is also written in Rust. Manticore itself is designed to be an allocation-free library. The goal is that you could take Manticore and drop it into an STM32, drop it into you name it, an Cortex-M class part, and be able to run it. We just also happen to have a secure operating system on top of this, underpinning the whole system, so that we can have a little higher assurance about the memory integrity of the system as we go.
So what kind of issues did you run into with getting a Rust application running within a microcontroller and a memory and flash space?
Honestly, the biggest issues for us have been code size. Specifically inside of Talk, there's a lot of use of generics, and this very rapidly bloats out your image. There's a lot of string handling inside of Talk for debug messages, which actually adds like tens of kilobytes of code size. And so as part of our work, we have gone in and created a build of Talk where it's stripped down. We remove a lot of the genericism from some of the pieces. We remove the debugging strings when we're building in release mode, and all the string handling, like Unicode handling in release mode. Those have been the main issues, is the flash pressure, to be honest. For Manticore itself, because we started the development of Manticore targeting this class of device, targeting an embedded system, it's actually very lean itself. It's a strong believer in zero cost abstractions, and so it is fairly small compared to what you might expect from a root of trust API implementation. Now, it's not complete. It's going to get bigger as we go, but we're at the size right now where things are looking fairly safe to be able to deliver the Talk plus Manticore package and still have room left over for other people's applications that they might want to run alongside of the root of trust API.
So there's like a standard API that Manticore is using to the rest of Talk. Does it just look like any other OS interface, syscalls and everything, or is it something special or different?
No, you're right. It is fairly straightforward. You have to provide your system implementation for Manticore. And so in the case of Talk, it wraps what's called libtalk RS, which is something that is being heavily developed by one of the engineers at Google as well. Jonathan Van Wy is actually working on redesigning that right now. It is just a syscall abstraction. There's only 5, maybe 6 syscalls in Talk. And so it just wraps these up and wraps up the driver interactions all underneath like a wrapper that you then have to provide to Manticore. You could wrap the Linux syscall API. You could wrap Windows system call API, or I guess they don't have a system call API. They have a system API, and be okay with that. It's very agnostic about where it's being run.
Okay. So how do you deploy these applications or changes to the root of trust firmware? Because presumably the BMC would be having to handle that and send the new firmware, the new applications over to the root of trust.
Yeah, so the way that we currently are doing it, and this is not the lifetime model of the device, this is just the way that it is currently being done in development. We sign a monolith, so if you want to update Manticore, you have to update the entire OS image. You then get the BMC to initiate an update. The BMC negotiates the download into negotiates with the RoT to download into Flash. It lays it out in Flash, and our secure bootloader is what's responsible for determining whether or not the system validated. So if you're thinking of like a loader 2 package, that's our secure boot process fills that role. The future holds us probably switching to a loadable application approach where we have worked enough on LVM that we have embedded pick, and we can move the applications around as we need to shuffle them and load them. We can independently update them in Flash, and then our loader 2 package becomes an application verification package and loading package that sits inside of Talk that independently verifies the apps before they're executed. But that is kind of our future vision. Right now, we are signing monoliths, which is very, very common. Like I don't actually know of many RoTs which are doing individual slice-based updates or app-based updates. If you're talking about things like smart cards or secure elements, they will have like a quote-unquote app-based update system where you can update individual Java card apps. And that's useful, and those are like very high assurance systems. They have a very clear abstraction for their operating system and for their runtime environment. We're trying to reach that same level of assurance through hardware support for secure boot, through our memory isolation inside of Talk, and through a very hardened kernel. So we're working to get there, but as I said, monoliths for now.
So is the core a Cortex M still, or are you using some other more
No,
advanced
the core for OpenTitan is actually, I don't know if I would call it an advanced new architecture. It is an interesting new architecture. It is our core is an RV32 IMC, so a RISC-V core. It is based off of the IBEX core, which is also a low-risk project. Before low-risk, the IBEX core was called, I guess I'm blanking on it, Zero Risky, there it is, Z0RO-R1SCY, Zero Risky. But once it became a low-risk project, it was renamed to IBEX, and it is a very small but capable RV32 IMC. So no atomics, single core, 32-bit, integer set, multiplication set, and compressed instructions. It's a very space-efficient core. And it actually also forms the basis for our big number accelerator. We have a big number accelerator that we call OTBN, the OpenTitan Big Number Accelerator, which has a larger multiplier at its core and an explicit call stack. And so that lets us do a little bit more integrity checking on the instructions that are being executed inside of OTBN. And it itself is based on RV32, but it's a different beast fundamentally. Yeah.
Okay. So have you ever thought through some more complex workflows? So you mentioned the validation of new updates. So like changing out what key is used to validate that, if you need to send a board back for RMA or transfer it to a new owner or decommission it in some way. Has that been defined yet, or are those workflows between the BMC and root of trust still to be defined?
So that actually is one of the biggest and I would say most intense areas of this project is ownership transfer. How do we take possession of a device? How does the silicon creator hand off this device to somebody, and that somebody can then be assured that only they and perhaps the silicon owner can then run code on it? And so we do have a fairly comprehensive model for ownership transfer. It's something that we've been working on before we actually started the silicon project side of things. Is there was designs being made for this ownership transfer model. We do have a cryptographic identity bound to the owner identity. Actually, it would probably be useful for me to link the document here. Sorry, I'm just trying to load it up on my machine. Maybe even screen share. Is such a technology even possible? Let's see. Can people see my screen?
Yes, although it's rather small.
Okay, yeah, sorry. This is a large display. So as part of our general documentation on OpenTitan.org, we have this document describing identities and root keys, and at the heart of it is this beautiful diagram, which Miguel Osorio, one of our security engineers, drew. It is absolutely gorgeous. I love this. So it describes individually what pieces go into creating an identity for the bootloader and kernel, which are silicon owner code, which is to say code that the person who is in possession, cryptographic possession of the device is allowed to run. There is a very clear derivation path for how the identity of the chip, the identity of the ROM and the identity of the ROM extension, which is ROM-like code living in Flash, all combine to form the actual owner root keys. And so this diagram, I won't walk through every block here, but you can see that there are OTP contributions, there's Flash contributions, there are private bus loaded versions of keys, and there are also gate contributions to these keys that are commanded by software but not visible to software in a lot of cases. And so we have a very controlled process for eventually deriving the owner root key. Now, what the owner root key is used for is up to the silicon owner. They're allowed to take this owner root key and turn it into version keys. Like you can fully implement dice on top of this. This is 100% dice compatible. And so when you want to then change an owner, we have a mechanism inside of our secure boot system which allows you to do a boot services request. You populate some persistent SRAM and then restart the device with a specific restart signal, and that causes our ROM and ROMX code to go and service this request to transfer the device to a different owner. And there are a couple different modes that this can take. If you can transfer it to an unknown state, which allows you to put it into like a nice transport ready state, or you can directly transfer it to another owner, which allows you to do a direct linked handoff to make sure nobody comes into possession of it in the middle. Even if somebody did come into possession of it in the middle, like was able to transition it to themselves, the goal of our secure boot and isolation model is to make sure that there is no identity that can be formed that matches any of the previous identities, such that you can't ever impersonate a previous owner or the next owner, and the next owner can't impersonate you. So we do have a fairly comprehensive model for this. And if you're interested in that, if you look for, actually, you know what, I'll just drop it into chat. I don't know if the chat actually is visible to people, but I'm going to do it. It's that if you look on OpenTitan.org for identities and root keys, you'll be able to find it there.
Awesome. Yeah, it sounds like it's really well defined. So what kind of, are there any other like security primitives that the root of trust could provide to the BMC that the BMC could use for like establishing its identity on the network, or like any sort of other crypto that we might want to use to secure the BMC itself?
Yeah, I think that there is. I think that most commonly you see a root of trust being described in a situation like this in order to provide the instruction integrity and machine identity. I have also seen integrations where the identity is based off of measurements of other components of the system. And so if you can measure and believe in the attestation of, sorry, not measure and believe in the attestation, if you can measure the BMC as it boots, you can then mix the version that you have witnessed into the identity that you're building. And if you can have the trusted BMC then report to you a version of the BIOS that it is going to provide to the next layer of the system, you can then mix that into the system, and you end up building this nice identity that is a composite of all the parts of the system. And I've seen this implemented now, and I think it is an interesting system, but it essentially like extends dice all the way from the top of the system down to the end of the system. I would say would be a good way of thinking of it, all the way up to kernel. The kernel, you could even mix the kernel identity into this. And so having that available to the BMC, having it be something that can be trusted to perform this mixing, this identity construction, I think is a very useful piece of infrastructure, because it lets you anchor an identity on a version stack of software inside the system.
So to build on that, is there also a unique identity assigned to each one of the roots of trust that the BMC can access?
So in the OpenTitan model, we have there's always a unique identity that the device possesses. It always carries a device ID written into OTP, and that is unique. That's never visible to anybody. You can never address the device by its device ID, because that is always mixed into its later identities as part of the measurements of the system, as part of the construction of its later identities. And so yes, there is a unique device ID, but no, you can't actually witness it. But that does still constitute a unique identity for that. Sorry, that helps you construct a unique identity, because at device creation time for the root of trust, you end up with a CSR, which you then later sign, which is the actual public half of the creator root key. And so you have an attested version of that key that you can now take off device and verify when the device attests later to a specific identity that it was in fact a real OpenTitan or an authentic OpenTitan stack that produced this attestation. Is that answering the question you asked, or am I rambling along the side of it?
Well, that answers most of it. Then the only other piece that I'd be wondering about is how we get that identity information into whatever system we're using to manage identities for, like, the whole production network, either at manufacturing time or when it arrives at the data center, like what that workflow looks like.
Yeah, that's a good question. So if it depends on how you want to frame your identity creation, I think. If you want to say that, so let's say I am a big computer manufacturer and I want to build 1 million units and I want to have an identity on these roots of trust, but I'm not selling directly to, let's say FANG, or I'm not selling directly to a consumer who's buying N million units. I'm selling to smaller shops that are buying a rack. They're not going to want to manage an RoT infrastructure probably, but we still want these machines to be secure. We still want them to be trustable. In fact, we might even want to be able to have them attest remotely later when we're doing remote work on them, or if we need to actually verify the authenticity of these machines for whatever reason. There is a flow here where the silicon creator for the root of trust mints the identities, and the integrator, the system integrator, then consumes the identity as they transfer the ownership to themselves. They take the device attests its transfer to them against the original identity that they saw from the manufacturer. They then put as they're putting this RoT on the board, they now have in their hand a chain which takes it back to being a certificate chain that takes it back to being a valid OpenTitan device, and they can trust the root of that chain, because it is fully attested in both steps, possibly even more steps, depending on how you want to do the transfer from the silicon creator to the silicon owner. Now, for somebody like Google, which is, buying more than a single rack of machines, Google itself probably wants to maintain the root of trust API infrastructure around this. And so the system integrator then puts the machines into transit state, unowns the roots of trust. And as the machines are being integrated into a data center, as they're being racked up and powered up, they are then starting to execute an ingest payload. And the ingest payload is responsible for taking ownership of the device, communicating the attested cert chain back to the infrastructure inside of the Google data center. And so Google ends up with a device which has a cert chain which attests to probably an intermediate certificate that is assigned to Google, because there's probably an intermediate ownership in there, but it can still believe in the authenticity of the stack on the device because they have this chain. It is also our intention to offer CRL so that if there is a case where we discover that devices have reduced integrity or have been compromised, that we can then later go revoke the trust in those devices as well. And so you could follow those intermediate steps and see the revocation higher up in the chain and say, oh, okay, these are no longer trustworthy devices. Our goal is to make sure that people aren't always eating OpenTitan PKI. We want people to be able to have their own PKI, because Google certainly will want to have that, and we believe everybody else will want to have their own stack. However, we're going to provide a reference PKI implementation based on this so that people don't have to reinvent the wheel every single time. Not everybody can take 20 Google engineers and have them build something. Sometimes you just want to have something off the shelf. But yeah, that's kind of our view on PKI.
So you mentioned a certificate chain that shows like ownership transfer, so Google or some other like large scale company can know that they like got an authentic OpenTitan piece of silicon. But what terminates that chain? What's the very start of it that you can trace the trust back to?
Yes, you trace the trust back to the silicon creator's root key. And sorry, I should clarify there. The certificate chain doesn't actually include ownership transfers. It just includes the intermediate development steps of that chain. You can't actually tell a device has been owned by a specific person just by looking at its attestation chain from the device. So there is a device, there is a signed by the silicon creator root key, which certificate, which shows this device as authentic. That device then turns around and signs the next layer, attests to the next layer in that chain, so that you can see the chain from the attesting software running all the way back to the silicon creator root key, if that makes sense.
Yeah, that makes sense.
Okay.
What else? So you mentioned the using USB 2 embedded or USB 3, and then I3C as some other possibilities for interfaces. Are there any others that have been investigated as the API for sending commands to the root of trust?
So, I mean, we have talked with some people about using something as kind of simple as UART. Our interface, our electrical API is really driven by what people are willing to integrate and what people believe that they are able to maintain signal integrity over. And so we ourselves have not come up with any new integration. We are just looking at what people are currently doing and saying, okay, well, we can build a root of trust which supports that use case. So I don't think there's anything else on the horizon right now that we've been investigating besides SPI with TPM, the TPM add-ons to allow for back pressure, that would necessarily form a new API for us, or an electrical API for us.
And is that prescribed by the OpenTitan group? Like they say you must use this interface or this API or this electrical connection, or is that more the role of an organization like OCP to define those standard integrations?
So we do have a set of standard integration guidelines. We call them admissible architectures. So architectures in which if you integrate OpenTitan into your system in this fashion, then you will have a system which is potentially secure. And so as part of our admissible architectures, we do currently specify only SPI as our integration path. And so there will in the future, I do not doubt, there will in the future be other integrations and we will come up with other admissible architectures where we demonstrate these other integrations. But currently we dictate, yes, if you want to build a secure system based on OpenTitan, you have to use this integration. And we have example integrations for multi-core machines, for single core multi-processor machines. Those are currently only accessible to our partners, but we are working to make some of that documentation available to the rest of the world. That's kind of something that's probably going to happen early next year as we start to open up some more of the documentation, the integration documentation.
So on the API level, then, is that something that OCP would specify, or is that more per customer, per integration?
So I think that there needs to be a central truth to an API, the API story, and I think that the OCP security specification is a very good step in that direction. I think that having Cerberus be an implementation of the OCP security specification would be a great step as well, because it would take something that is already, as we understand it, a widely deployed root of trust API and put it in a position to also be the lessons learned story for the OCP security specification. So I think that yes, OpenTitan should not own the root of trust specification. OpenTitan should try and contribute to it, and we should definitely try and work with other people who are developing it. But I think that there needs to be a central place where there are industry players who are working together to build this, and I think OCP would be OCP is a good place for the OCP security specification to be developed. If you look at what we're doing right now with the Cerberus specification with Microsoft, we're actually inside of the Open Compute Project /security repository working on trying to hash out some of the details in that specification there. And so I think that there is a definite point in the future where the two combine or meet up in a more significant fashion, and we can say that yes, Cerberus is an implementation of the OCP security specification. But that's not today. I think that's a good future point to aim
for. Cool. Yeah. Looks like we're close to the end of our time slot. Are there any more questions for us that we can? Anything else that the audience wanted to discuss or?
There haven't been any other questions posted.
Okay.
Maybe we'll give people a second here to try and type frantically, or maybe we should have expected that they would have been typing all along. All right, I feel like ending 5 minutes early isn't outside of the realm of possibility, just to save people from me monologuing. Unless there's any other questions, I'm happy to call it here if you are, Benjamin.
Sure. Yeah, I think I brought up everything I wanted to.
All right. Thanks for your questions. They were really good.